Hello, everybody. Here we are in Chapter 5. Chapter 5 is, as I told you, the most intimidating chapter in the textbook for now. You'll see some big ones later on, but I think it's great. I think finally we're going to put all this chemistry that we've been doing, which maybe some of you are bored stiff of saying, "Oh, I know all about chemistry." We need to start to build these macromolecules that are then going to enable us to create things within cells and then create cells themselves so that we can create life. We're only going to go over 5.1 right now, and I'll talk to you about how the chapter is structured. Yes, it is the middle of summer, and yes, I went hiking today, so yes, I'm wearing a hat in school. Sorry you aren't. Well, all living things are made up of 4 classes of these large biological molecules. What are they? Remind yourself. Press pause. Do you remember what the 4 major macromolecules are that make up all living things? You learned about them in 10th grade biology. Here they are. Here's chapter 5.1, what we're going to be doing, and then you're going to see that there's probably 3 or 4 pages on each of these, maybe 4 or 5 pages on some of them. Carbs, lipids, proteins, nucleic acids, and you can see those. We're going to go over each of them in detail. While chapter 4 was small, this chapter is big. It's going to take at least a week, maybe a week and a half, and then we're going to test. So chapters 4 and 5, that's it, and then we will test. So please stay up in terms of the workload. Don't get behind. I would say get ahead, if anything, because chapters 6 and 7, we're going to start to talk about cell membranes and then organelles, and we're going to start to build cells because now we've finally put all of these big macromolecules together. There's a lot of interesting stuff here, so have an open mind and enjoy. I'll try to make it interesting for you. I will tell you this. We're going to go over some learning targets, but do not write anything down for them. We'll just do them verbally. There's a lot here. The Cliff's Notes is huge with respect to this chapter. There's many concept check questions. I like every page in here as far as what's going to be covered on the AP biology test. And there's definitely a ton of movies too. There's one for each one of these. There's a lot here. So do not wait, I guess is my thing. I would say just, what I would say is if you were in class, I would say stay with me. I would say today 5.1, tomorrow 5.2, or however it's going to be organized. I don't know how it's going to look this fall. However it's going to be organized, stay with me. You don't have to get ahead of me unless you'd like to do that. Some kids like to do that where they will like read the section. I'm very transparent as to what we're going to be doing on a daily basis, and they'll read the section that we're about to talk about, say in lecture, and so they have an idea of what I'm about to say, and then maybe that's better for them. Other people like to wait and then have me spoon feed it to them, and then it's easier when they go to the textbook. But what you don't want to do is get behind so that you're catching up, or the night before the exam, you're actually doing work. The night before the exam, you should be completely done, and you should just be reviewing, just putting it all together, maybe the 2 or 3 nights before the exam. That's in a best case scenario. I get it. That's how it would look. Maybe in college, you'll actually have more time. That's what lots of kids tell me when I talk to them and they've gone away to school, as they say, oh my gosh, my junior year or my senior year of Battle Mountain was the hardest academic year because the bell rings and I go to another AP or DE class, and it never stops. But in college, you'll have these big gaps of time during your day that you've built in, and that's a great time to go to the library and get ahead or start to study for a test a few days out. So anyway, you'll figure out what's best for you. That's part of this whole process. It's not supposed to be easy. I don't think a lot of you have really been tested academically, so Chapter 5 is going to do it. Ask anyone who's taken this class before. Well, here we go. We got to put stuff together. The small organic molecules are joined together to form larger molecules. So here are 6 amino acids. These are just example amino acids. Let's imagine that we want to put them together to make a larger molecule. So here they are. Let's add them together, and what would we get? All together now. Good job. A protein. That's right. Amino acids put together make proteins. You can see this ribbon structure here. This is This is exemplary of probably like hundreds of amino acids that have come together to make this protein. Remember that form equals function. The form that that ribbon structure has dictates what it does in biologically in any organism. So it's no coincidence that it looks that way, and it looks that way because of the monomers of these individual units that we're going to put together to make a polymer. So macromolecules are polymers built from monomers, and these monomers are covalently bonded. That's why we went over covalent bonds so much. We need to start putting these individual things together to make longer things, like the amino acids coming together to make a protein. The analogy I'm giving you here is this, I guess, is this a metaphor? Is this long train? If an individual car is fine by itself, but let's stick a bunch of them together, and then we get something that's going to be efficient for the train company to pull. There are trains that are over a mile long that come out of these coal extraction areas, like in the Powder River Basin in Wyoming, for instance, and then they drive down the Colorado River, and they go out through western Colorado, out through Fruita and Westwater, and then out into the Nevada desert, Utah, and then eventually the Nevada desert. But the point is they're really long, and individual cars are fine, but let's put a bunch of them together. That's called a polymer. Poly means many, mono obviously means one. So how do we do this? Well, this is a picture directly out of your textbook. And you can see here, if we have a polymer and we want to keep adding monomers to it, what do you see is released when a monomer is bound to a polymer? Well, this is called the dehydration reaction. Go ahead and pause it if you need to and write this down. When we want to add monomers together to make a polymer, water is released. You can see that. And we get a longer polymer. You can see that the hydrogen atom came from one of the monomers, and the hydroxyl group came from the other, and two H's plus an O makes H2O. So there it is right there. This is called dehydration. You can think that water is leaving. Sometimes you've probably been dehydrated. Water has left you. Well, water is leaving the growing polymer. See that right there. Well, here's a real world example. When plants make glucose through photosynthesis, they can either store it as starch, usually in their trunk or their roots, and sometimes we eat starch bombs, such as like carrots or potatoes or beets or onions or things like that. They have tons of starch. They're just repeating subunits of glucose, or they can build structural material called cellulose, and this is the primary component in cell walls. And in fact, I once read that there's like 1 billion pounds of cellulose created on our planet every second. And the idea is that plants take the glucose monomers and through dehydration reaction, put them together to make long polymers, wind them up, and they become really strong, and it helps to make the wall of the plant cell. I know it's pretty riveting. Let me show you one final example. We're going to make a carbon snake here using the dehydration reaction, which just means that water is going to be liberated. You're going to see that as steam. And we're just going to put together table sugar and sulfuric acid. Please don't do this because it creates a super dangerous, I guess, noxious gas, and it's a lot of heat that's liberated. It's exothermic reaction. Here it is. It's pretty exciting. Let me turn down the volume. Yes, I know that's pretty crazy. Okay, let's imagine here that you eat a big meal, so that you have all these polymers from all these things that you've eaten. Like, let's say you have a steak dinner with potatoes and so on, and you have proteins, you have carbohydrates, you have nucleic acids, you have lipids, and you have these big long polymers, and you need to break them down. What do you think you're going to use in order to cut each monomer from the longer polymer? You're right, water. We're going to use water. And then what we do, that this is why you get thirsty when you eat, is because your body's like, okay, sweet, we got these long polymers, but we need to break these things into individual monomers, so then I can use enzymes to create the polymers that I want in my body, a different type of lipid or a different type of protein or carbohydrate, for instance. So if we have a long polymer and we want to break it down, go ahead and write this down. Hydrolysis reaction is where it's at. We're going to break down a polymer by adding water. So I guess to come back to my example here, let's imagine that we have the train and we added water to the coupling between each of these cars. Maybe we can break them through a hydrolysis reaction. Remember, hydro means water, and to lyse something means to cut it. So here's a picture from your textbook. You can see up here between monomers 3 and 4 on this polymer. We want to cut those and get that individual monomer off. We're going to add water. And you can see here that a hydrogen atom is put on one of the monomers of the bond to be broken, and the other monomer gets the hydroxide functional group. Hydrolysis adds the water molecule breaking a bond. Polymers are disassembled by hydrolysis, a reaction that's essentially the reverse of the dehydration reaction. So go ahead and stop, press pause, go over dehydration and hydrolysis reactions right now, please. I know it's pretty exciting. What you saw there is it's called the ester linkage, where an oxygen is between two monomers, for instance, and it's covalently bound. And we're going to break that ester linkage, give it a hydrogen atom, so that the one hydroxide group goes to one monomer and the other hydroxide group from the water molecule goes to the other monomer. So we're just doing the reverse here. Let's imagine that we're breaking our protein into the individual amino acid parts. Well, that's it for now. Go ahead and press pause. Think about these learning targets. And then next time I see you, we will go over carbohydrates. Thanks.